Problem 2 is compound interest. Okay? We have the balance, the principal, the annual interest rate, the number of times the interest is compounded per year, and the number and the time in years. Now again, we're just going to take the information from the word problem so that we can substitute that into our formula. Okay? So we need to identify each one of our variables. Okay? So the first thing we want to do is we want to know that A, the balance, is what we're solving for. Oh, well, let me just read the problem first. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5 interest compounded monthly. What will the account balance be after 18 years? Okay? So, the account balance is what we're looking for, right? So what will the account balance be? That's our A. So A is our account balance. Account balance. The principal, P, is the initial deposit. The initial deposit here was what? $2,000. So that's 2,000. The R is our annual interest rate expressed as a decimal. Okay? So the annual interest rate is what? 4.5%. Written as a decimal would be 0.045. Okay? So R is 0.045. Let's see. The N is equal to the number of times the interest is compounded per year. All right. So it says it's compounded monthly. So how many times per year is that? 12. Very good. So that's 12. And then the T is the time in years, which is 18 years. So now we substitute our values in to this equation right here. There's our equation again. So A is equal to the principal, which is 2,000, times the quantity of 1 plus the R, which is 0.45, divided by the N, which is 12, all raised to the 12 times 18. So now we simplify. So A is equal to 2,000 times 1 plus 0.045 divided by 12. And I'm going to write that whole number, okay? 0.00375. 0.00375. And then 12 times 18. Thank you. 216. Okay? So now we've got 2,000. Oh, I guess I could have added this at the same time. 1.00375 to the 216th power. All right. So now the exponent. So 1.00375 raised to the 216th power. So let's round it to the nearest hundredth. Okay, let's round to the nearest hundredth. So this will be 2.24, right? So we've got 2,000 times 2.24, and now that's what we're going to multiply. So 2,000 times 2.24 is equal to 4,480 what? Dollars. Exponential decay is the same exact thing except what? Here, it's the growth factor or the decay factor is 1 minus the percent rate of change expressed as a decimal. So it's the same thing except for that one little difference. Okay? So problem 3 is modeling exponential decay. A kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meters increase in altitude, the pressure decreases about 11.5%. So what is the approximate pressure and altitude at an altitude of 5,000 meters? So again, the first thing we need to do is figure out our x, y, a, and b. So we're going to let x be equal to the altitude. It's going to be equal to the altitude in thousands of meters. So here, the altitude that we're searching for is at 5,000 meters. So we're going to say that x is equal to 5. Y is the approximate pressure at 5,000 meters. So the approximate pressure at 5,000 meters. A is the initial pressure, which is 101 kilopascals. So this is going to be 101 kilopascals. And of course, B is going to be our decay factor. And so remember, the decay factor is 1 minus the rate of change. So the decay factor is going to be 1 minus 11.5 written as a percent. So that's going to be 0.115. So 0.115, and when you subtract that, you get 0.885. That is your decay factor, and that is your B, 0.885. So now we can substitute in all of our values into our function. So we've got y is equal to the A, which is 101, times B, which is 0.885, all raised to the x, which is the altitude of 5. So we've got 0.885 raised to the 5th power, and we're going to say that is 0.54. 0.54. So 101 times 0.54. So 0.54 times 101, and that equals 54.54. So 54.54 kilopascals. So how does the graph of an exponential decay function differ from the graph of an exponential growth function? How are they the same? Well, if you take a look at the graph, the exponential decay graph decreases from left to right. The exponential decay decreases from left to right, while the exponential growth graph increases from left to right. And also, both graphs approach the x-axis, and both graphs have a y-intercept of 0, a. And when I say approach the x-axis, I mean they approach the x-axis, they theoretically come closer and closer and closer and closer to the x-axis, but they do not touch it.